Have you ever noticed how sometimes you can hear a faint conversation through a wall really clearly?
Hmm.
But then if you're underwater, even loud sound nearby gets kind of muffled.
Yeah, it's quite different, isn't it?
Or like feeling a train coming through the tracks way before you actually hear the whistle through the air.
Exactly. That's a perfect example.
It feels like sound has these multiple personalities almost.
Mhm.
Its speed just changes drastically depending on where it is.
Yeah.
So why is that? Why does sound travel at such, well, wildly different speeds?
It's a really great question, actually, and understanding it helps us understand, a lot about the physical world around us. So today, for this deep dive, we're going to really get into the science behind sound velocity.
Okay.
We'll look at how sound waves move through different stuff, solids, liquids, gases, and crucially, what properties of those materials really control how fast sound can, well, zip through them.
Right.
The mission really is to grasp the core ideas and see how they sort of manifest in the world.
Okay, let's unpack this then. Starting with the absolute basics. Sound, it's not like light, is it? It needs something to travel through.
That's the fundamental difference, yeah. Sound is what we call a mechanical wave.
A mechanical wave, okay.
Think of it like ripples spreading on a pond. You absolutely need the water for the ripples to even exist.
Oh, yeah.
Sound needs a material medium, something physical to vibrate and pass the energy along.
So it needs stuff.
It needs stuff, exactly. Light, being an electromagnetic wave, doesn't need a medium. It can travel through the vacuum of space.
Oh.
And because sound relies on that physical medium, its speed is inherently, tied to the properties of that medium itself.
Makes sense. It's all about the material.
Yeah.
Now, isn't there a basic equation for any wave connecting speed, frequency, and wavelength?
That's right, the universal wave equation. It's our sort of blueprint. V.
V.
Yeah, V is the velocity, the speed.
Oh.
F is the frequency, how many waves pass a point each second. And lifts, lambda, is the wavelength, the distance between peaks of the wave.
Simple but powerful.
Very. It applies to all waves.
But okay, that describes a wave. Zooming out, what are the big picture properties of the medium itself that dictate the speed? Like, what makes steel so different from air for sound?
Right. This gets to the core of physics. For a mechanical wave like sound, its speed is fundamentally governed by two main characteristics of the medium it's traveling through.
Okay, two things.
First, there is its elastic property. This is about how easily the material gets deformed, but also, crucially, how well it springs back to its original shape.
Like stiffness.
Exactly, like stiffness, how quickly it recovers. The second property is its inertial property. That's essentially its density, how much resistance it puts up against being moved, against changes in motion.
So elasticity and inertia, or density, needed to spring back fast, but also be, easy to move? Low inertia.
Precisely. High elasticity means the vibrations get passed along efficiently. Lower inertia or lower density means less resistance to that vibration actually happening to the molecules moving.
Okay, that makes sense.
And this leads us straight to the general formula. V.
See.
Yeah. E represents the modulus of elasticity, that stiffness factor, and rho is the density. So generally, higher E, lower O means faster sound.
Got it. Higher stiffness, lower density, faster sound. Let's test this out. Solids. I've always heard sound travels fastest through solids. Is that mainly the elasticity?
Primarily, yes. Their elasticity is incredibly high. For solids, the specific E we usually look at is the Young's modulus.
Young's modulus.
It measures how much a solid resists being stretched or squashed lengthwise. Solids are just very, very stiff compared to liquids or gases. Their Young's moduli are enormous.
Oh, so give us an example, like metal.
Iron. Let's take wrought iron, yeah. Its Young's modulus is huge, something like 197, 109 newtons per square meter, almost 200 billion.
Wow.
And its density is about 7,850 kilograms per cubic meter, if you plug those into our ER formula.
Let me guess, it's fast.
Very fast. The calculation gives you roughly 5,009 meters per second.
5,000 meters per second, so 5 kilometers every second.
Exactly. And that matches experimental measurements really well, which are around 5,000 meters.
That's incredible. That really explains the train track thing then. You hear it through the steel rail miles away because sound is just screaming through the metal that fast.
Precisely. The steel is just a fantastic conductor for sound waves because of that high elasticity.
And you mentioned seismology earlier. Is this why earthquake waves travel at different speeds too?
Absolutely. Seismologists rely on this. Earthquakes generate different types of waves, like P waves, primary, and S waves, secondary, which travel at different speeds through the Earth's layers because those layers have different elastic properties and densities.
Ah, so they time the arrivals.
Exactly. By timing when the faster P waves arrive compared to the slower S waves at different locations, they can pinpoint the earthquake's origin, its epicenter. They're using the Earth like a giant sound lab.
Fascinating. Okay, so solids are super elastic, super fast. What about liquids? They're obviously less rigid. How does that affect the E in our equation?
Good question. For liquids, Young's modulus doesn't really apply because they don't resist stretching in the same way. Instead, we use the bulk modulus.
Bulk modulus, okay.
This measures resistance to compression. How much does the volume change when you squeeze it under pressure? Liquids resist compression much more than gases, but less than solids.
Right, so let's take water. What does the speed look like there?
Okay, water at, say, room temperature, around 27 degrees Celsius. Its bulk modulus is about 2.0509 nanometers Celsius. Still billions, but less than the iron.
And density.
Density is around 995.5 kilomicroliters a second, just under 1,000.
Okay, so plugging those in.
You get a velocity of about 1,433 meters per second.
1,433 meters.
Yeah.
Still way faster than sound and air, but definitely slower than in the iron.
Exactly. The experimental value is actually a bit higher, around 1,498 meters at that temperature. Our simple model is imperfect. Other factors can play a role, but it gets us in the right ballpark.
Okay, but the trend holds. Solids fastest, then liquids, which implies gases are the slowest.
That's the pattern, yes. Liquids are faster than gases, but generally slower than solids. It really underlines how much the medium matters.
And you said gases have a particularly interesting history, something about Newton.
Oh, yes. The story of figuring out sound speed in gases is, well, a classic piece of physics history. It involves a brilliant first attempt and then a crucial correction about a century later.
Intriguing. So in gases, sound moves as compressions and rarefactions, right? Like pushes and pulls in the air.
Exactly. Longitudinal waves. Little regions where the gas molecules get squeezed together, compressions, and regions where they spread apart, rarefactions, propagating through the gas.
And Newton's first idea.
Well, Sir Isaac Newton, naturally, tackled this. His initial assumption was that these compressions and rarefactions happened isothermally.
Isothermal, meaning constant temperature. He thought the temperature didn't change during these rapid squishes and stretches.
That was his hypothesis, yes, that any heat generated during compression would instantly dissipate, keeping the temperature constant.
Okay, so if temperature was constant, what did that mean for the elasticity, the E in the formula?
Under that isothermal assumption, the math works out such that the modulus of elasticity E is simply equal to the pressure P of the gas.
Ah, so his formula became V, just pressure over density.
Exactly. VF. Seems straightforward, right?
Seems plausible. But you said there was a problem.
There was a significant problem. When Newton, or others later, plugged in the values for air standard atmospheric pressure and the density of air, the velocity it predicted was too low.
How low?
Considerably lower. The measured speed of sound in air at 0 degrees C is about 330 meters per second. Newton's formula gave something closer to 280 meters per second. That's, a pretty big miss, off by about 15%.
Right, not just a small error. So his isothermal assumption must have been wrong. Who figured it out?
It took about a century, but the French mathematician Pierre-Simon Laplace cracked it.
Laplace. Okay, what was his insight?
Laplace realized that those compressions and rarefactions happen so fast in a sound wave that there's simply no time for heat to flow in or out. The process isn't isothermal, it's adiabatic.
Adiabatic, meaning no heat exchange. The heat generated during compression stays put, and the cooling during rarefaction happens in isolation.
Precisely. It happens too quickly for thermal equilibrium to be maintained with the surroundings.
And how did that change the elasticity term, the E?
For an adiabatic process in a gas, the effective modulus of elasticity isn't just P, it's gap. Gamma times P.
Gamma. What's gamma?
Gamma is the ratio of specific heats for the gas. It's a property of the gas itself that relates to how its internal energy changes with temperature under different conditions, like constant pressure versus constant volume.
Okay, a property of the gas.
Think of it this way. Because the heat can't escape during compression, the temperature does rise slightly in those compressed regions, making the gas resist the compression more strongly than it would isothermally. It effectively makes the gas stiffer for these rapid changes.
Ah, so the adiabatic process makes the gas act stiffer, leading to a higher effective elasticity.
You've got it. So Laplace's corrected formula became V-iet.
Yet. including that gamma factor. And did that work?
It worked beautifully. When you use this formula, plugging in the known value of gamma for air, which is about 1.40, the calculated velocity matches the experimental 330 meters almost perfectly.
Wow. That's a fantastic correction, a real aha moment. It shows how subtle thermodynamic details can be critical.
Absolutely. It confirmed sound propagation in gases is an adiabatic process, not isothermal, and resolved that long-standing discrepancy.
So gamma is key for gases. But what about the overall temperature of the gas itself? Does that still affect the speed, even if the process is adiabatic?
Oh, definitely. The ambient temperature is still very important because it affects both the pressure and density of the gas, although in a related way through the ideal gas law.
How does it relate faster and warmer air?
Yes. For a given gas, the velocity of sound is directly proportional to the square root of the absolute temperature measured in Kelvin. So V euros/S.
Okay, so warmer gas, faster molecules bouncing around, faster sound.
Essentially, yes. If you know the speed at 0 degrees C, 330 meters, which is 273 Kelvin, you can calculate it for, say, a warm day at 30 degrees C, which is 303 Kelvin.
And that would be?
Crunching the numbers using that square root relationship gives you about 348 meters. A noticeable increase.
Makes sense. You can almost hear the difference on a really hot day versus a cold one, maybe? Or is that just perception?
The difference is there, though. Atmospheric conditions like wind and humidity also play significant roles in how we perceive sound over distances. But the base speed definitely increases with temperature.
We can even calculate that gamma value for air using the known speed, right?
We can. If we take the experimental speed at 0 degrees C, 330 meters, standard pressure, 10 m, and the density of air at STP, 1.293 kilojoule mole in the water, we can rearrange Laplace's formula to solve for gamma. Plugging in the numbers, 1.293 tau, it comes out to almost exactly 1.40.
Which confirms the accepted value for air. Neat.
It all ties together very nicely.
Okay, so let's recap this journey. We started with the basic idea that sound needs a medium.
A mechanical wave, yes.
But its speed depends fundamentally on the medium's elasticity, how well it springs back in its density, or inertia.
VER, that core relationship.
Then we saw how E changes. Young's modulus for solids, making them super fast conductors.
Like iron at 5,000 meters.
Bulk modulus for liquids, slower but still fast.
Water around 1,500 meters.
And then gases, where Laplace's adiabatic correction, adding that gamma factor, was crucial to match experiments.
Right, showing that VH bar and explaining why sound travels around 330 meters in air at standard conditions, increasing with temperature.
It's amazing how understanding these specific properties unlocks the why behind those different speeds we observe.
And it's not just, interesting physics trivia. This precise knowledge of sound velocity is absolutely critical in countless real-world applications.
We touched on seismology.
Absolutely fundamental there for mapping the Earth's interior and locating earthquakes, but also in acoustics designing concert halls so sound reflects and travels predictably for the best listening experience.
Right, you don't want echoes arriving at the wrong time.
Or designing noise-canceling headphones, which rely on precisely predicting and interfering with incoming sound waves.
And you mentioned medical ultrasound, too.
Yes. Ultrasound imaging relies entirely on sending sound waves into the body and measuring the echoes that bounce back. The speed of sound varies slightly in different tissues: fat, muscle, bone, fluid.
Ah, so the machine uses those different travel times to build up a picture.
Exactly. Knowing the precise speed of sound in different tissues is what allows the machine to accurately map out internal structures and diagnose medical conditions non-invasively. It's truly remarkable.
It really is. It makes you think. If understanding something as seemingly basic as the speed of sound has led all these insights and technologies.
It does raise a fascinating question, doesn't it? Considering how fundamental sound velocity is to so many natural phenomena and technologies, what other hidden properties of our world might we uncover just by looking more closely at how things move, even at this very basic physical level?
Something to ponder. There's always more beneath the surface, isn't there?